In this video, we're going to be studying what's called quantum numbers. In the previous video, we saw orbitals and how we use how electrons are no longer found in specific orbits as dots, but instead we now view electrons as essentially being found in a region of probability that we call an orbital. And we saw different shapes of those orbitals to describe what the electrons in an atom would sort of look like. And so these are the different shapes here, and they're all based on wave equations from scary Schrodinger over here. And they're really just probability distributions where you see some probability of the electron existing at some distance from the nucleus 90% of the time. And that's what the orbitals are. And we saw that there were different shapes, S, P, D, and F, and that they can exist at different energy levels. If that doesn't ring a bell, please make sure you go back and watch the first video in this lesson on atomic orbitals. If you are comfortable with atomic orbitals, now you're going to be able to understand the quantum numbers. So rather than draw out these orbitals every single time like this and explain them in these complex ways, we can now use a set of numbers to describe the general probability region for an electron, almost like an electron's address. It won't tell you exactly where the electron is at that specific moment in time because you can't do that based on Heisenberg's uncertainty principle, but it'll give you some general idea. Like it can say this person is located on planet Earth in Canada, in Ontario, in Burlington. So I can kind of tell you that same idea for the electron. I can say it's found in energy level 2, in sublevel P, in the specific orbital of P called Px. So I can give you details like that in the form of these numbers, almost like an electron's address. And these are called the 4 quantum numbers. Essentially, they're a nice numerical and an easy way to describe electrons and their orbitals. So let's go take a look at the first quantum number. That's called the principal quantum number. We represent that with the letter n. And that principal quantum number just tells you what shell the electron is in. What is the energy level that you're in? And we can have values such as n is equal to 1, 2, 3, 4, so on and so forth. And then n is equal to 1 is the lowest energy level that you can have. You can't have n is equal to 0. You need to be in an energy level. So lowest energy level. So again, it's just really the shell that you're in. And the cool thing about the principal quantum number, n, is that it also describes the size of the orbital. If you remember from some of the visuals we saw, if you were an s sublevel orbital, in n is equal to 1, it was a small sphere. If you were an s and n is equal to 2, it was a larger sphere, and then larger and larger and larger and larger as you go higher up in the shells. And so essentially, the higher the value of your n, the higher the probability that the electron will be found further from the nucleus, so farther away from the nucleus. And that also means that the higher the energy in that electron, because if you're farther away from the nucleus, you're easier to access and to be removed. You're not being held down by the nucleus as strongly as the ones that are closer to the nucleus, right? And there's electrons in between you and the nucleus, the farther out you are. So the larger value of n means you have a higher likelihood of being found farther away from the nucleus. And the neat thing about this first quantum number is that it's going to be used to find the next set of the next quantum numbers. So the next quantum number that gives us more detail as to where the electron is called the secondary quantum number. We represent it with the letter n. And what that does is it tells you the shape of the orbital that you're in. In other words, it tells you the sublevel or the subshell or sublevel. It basically tells you if you're in an S, P, D, or F sublevel. How do we figure this out? How do we know this? Let's do a few examples and let's see what the possible values of L are. Whenever you're trying to find the possible values of L, they are going to be equal to anything from 0 all the way up to n minus 1. So let's look at a case where we are in energy level 1, n is equal to 1. If I want to find the possible values of L there, I'm going to start listing all the values from 0 all the way up to n minus 1. So I'm going to list 0 and I'm going to stop. And the reason is because n minus 1 in this case is 1 minus 1, which is 0. So that's all I can have. And what does that L mean? That L means I'm in sublevel S. So whenever you see L is equal to 0, if I tell you the electron has L is equal to 0, that means it's in sublevel S. So this electron that I'm trying to describe is in energy level 1, sublevel S. And that makes sense. There's only S in energy level 1. Now, let's do the same thing for energy level 2. Energy level 2, if I want to find the L values, L is equal to 0, 1. And I stop there because in this case, n minus 1 is 2 minus 1, which is 1. So the L would be the S sublevel at energy level 2 because there's an S in there. But then you also have another L, which is 1 here. And that would be P. That's where the P first comes in. So if I say your L is equal to 1, that means that you're in the P sublevel. We'll try the same thing, but for n is equal to 3. So when n is equal to 3, our possible L values are 0, 1, and 2, and we stop. That's because n minus 1 is 3 minus 1, which is 2 in this case. So we can go all the way up to 2. So in the third energy level, there's a 0, which is S. There's a 1, which is P. There's a 2, which is, you guessed it, D. We'll do one more. Let's do n is equal to 4. So our possible L values there in n is equal to 4, and a lot of you can already list this, is going to be 0, 1, 2, and then 3. Because in this case, n minus 1 is 4 minus 1, which is 3. So that 3 means F. So in the fourth energy level, we have S, P, D, and F. And that's what we're filling out there. So that is our secondary quantum number. We're getting more specific with where our electron is. So the principal quantum number is like saying, I'm on Earth. The secondary quantum number is like saying, well, where on Earth? In Canada, maybe. So I'm zooming in a bit more. But we could get more information. This is still a bit general. We can actually zoom in a little bit more to find out some more information about our electron. And so there's another quantum number called the magnetic quantum number. It's the third one based on L. We call this ML. And that tells you what orbital you're in within the subshell. So which orbital are you in within the subshell? So for example, let's say I have a subshell over here. You might already be able to guess what this is. There's 3 orbitals there, so you know it's a P subshell. So this is L is equal to 1, okay? And that means it's a P subshell. I didn't specify what energy level it's at. It could be an energy level 2, 3, 4, so on and so forth. It couldn't be in 1 because, well, there's no P in the energy level is equal to 1. But here we have a P subshell, and within the P subshell, there's 3 P orbitals. There's the Px, the Py, and the Pz. So this ML value here that we're going to figure out will tell you which one you're in. Are you in Px? Are you in Py? Are you in Pz? That's what it's going to tell you. So how do we figure this out? Well, the ML value is going to be a range that goes from negative L all the way to positive L, including 0. So let's do the example with P first, and then afterwards we'll do the other ones. So if we are in the subshell P, that means our L value is 1. That indicates that we're in P. The possible values of ML are going to be from negative L to positive L. So negative 1, 0, positive 1. And that's what these represent here. We have negative 1, 0, and positive 1. You do have to put those signs there. Okay? So if I tell you I'm in energy level 2 in L is equal to 1 and ML is equal to negative 1, I told you that I'm in this box over here. I told you I'm in energy level 2, sublevel P, and then that first box there. In reality, you could actually write the negative 0 and plus 1 in different orders because these are all degenerate, meaning they're the same energy. But by convention, we usually put negative 1, 0, and positive 1. So these represent the number of orbitals in the P subshell, which is simply 3 orbitals, 3 boxes. We can do the same thing for S. So for S, the value, L is equal to 0. And there's no negative 0 or positive 0, so there's only one ML value, 0. There's only one orbital. If you remember from S, I'm drawing this in a different order, but it's okay. This is what an s is. That's it. There's only one box. That makes sense. Let's try the same thing for the d orbitals now. Remember, d is 2 for L. So the ml is going to be -2, -1, 0, +1, +2. And if you count these, you have 1, 2, 3, 4, 5. 5 orbitals. And that if you remember, is just like what we drew above over here in our first video. Remember when we drew the d subshell as boxes? Look, we have 1, 2, 3, 4, 5 boxes. We have a -2, -1, 0, +1, +2. Those are the boxes within the d sublevel or subshell. Those are the orbitals within there. So we can do the same thing for F. L is equal to 3. And you can probably guess, oh, there should be 7 numbers for ML because there's 7 boxes in the F orbital. If you look up here, we have 1, 2, 3, 4, 5, 6, 7. 7 boxes. And that's because we have those 7 numbers here. So ML values are going to be -3, -2, -1, 0, +1, +2, +3. And that's 7 orbitals within there. So now I gave you more detail. I said, you're on Earth, Canada, and then Ontario, right? So I told you the specific box that you're in when you did that. Now there is a problem though. These quantum numbers, we want to use them to describe a specific electron. Remember that within a box, you can have a maximum of 2 electrons. So if I left it at these 3 numbers here, I'm not describing 1 electron, I'm describing 2. And I don't know which one I'm talking about. They can't all have the same quantum number in there, right? Otherwise, they're the same electron. If I give them the same exact quantum numbers, it means that they're at the exact same spot, at the exact same time, and that's not really possible. So scientists said, you know what? We need another number to tell the 2 apart within that box. Okay, we need something else to tell them apart. So, because they're different electrons at the end of the day. So if we just kept these 3, we are just describing the 2 electrons in a box, but let's have one more to really distinguish between 2 electrons there. That brings us to our 4th quantum number, the spin quantum number, or ms. And so the spin quantum number solves a problem of the 2 electrons per box. In a simplified sort of way, what it means is that the electron is spinning. Now, it's not really spinning. It's more the effect it has on magnetic fields that we're looking at here. But we can think of it as it's spinning. It's like almost like when you're spinning rotating a basketball on your finger, for example. It's rotating in some way. But it's really based on the magnetic fields. So there's really 2 spins that an electron can have. You can either spin up, or we say also spin down. So you can spin up or spin down. Okay. So I'm going to draw 2 electrons, one spinning up and one spinning down. So just to show you this, let's say we're going this way for this one. The other electrons going the other way. So in a box, the electrons will have opposite spins. As you saw in the previous video, I started representing electrons as arrows, and I didn't really tell you why. I just said just accept it for now. And I had opposite arrows in the box. That's because within the box, one electron will be an up spin, and one electron will be a down spin. They can't both be the same spin, otherwise they're the same electron. So they can't be the same spin. They have to be opposite spins within the same orbital, the same box there. Okay? So within a box, if you have 2 electrons, one spins up, one spins down. The up spin we can represent as a up arrow, and then the down spin we can represent as a down arrow. Some people will sometimes draw the arrows as half arrows. It makes it look nice and neat within the box. So little half arrows like that instead. So how do we represent this with numbers though? Because these are quantum numbers. We don't want to write up, down, or little arrows all the time. So the spin up is represented by the value plus half, and the spin down, probably guessed it, minus half. So we have our spin up and spin down with plus half and minus half. So since there's only 2 possible spins, That's why we really only have a maximum of 2 electrons in each orbital, in each little box. And that explains that. So to summarize what we just saw with these quantum numbers, we're going to do an example. I'm going to draw out some electrons for an atom, and we're going to determine the quantum numbers for a specific electron in that atom. Okay? Let's take a look at this atom over here. This atom, you can tell, has electrons in a 1s sublevel, also electrons in a 2s sublevel, and electrons in 2p. There's some here in this orientation, in this orientation, in this orientation. So we're going to draw this out. Let's do that. So I'm going to do the first shell over here will be the first box, the 1s. Okay. And I'll put its 2 electrons as 2 arrows with opposite spins. And then the ones that are 2s and 2p, that's my second shell. So let's go do that. So let's put this is a 2s, so an s in the second shell. And then this is a 2p, so a p in the second shell. That's where it starts. And that's it for this atom. That's all you see in this drawing. And I'm going to go ahead and put in the electrons. Okay. And we're going to determine the quantum numbers for a specific electron. Let's do it for a couple, but we'll start with one. We'll start with this one over here. I'll circle it. This is the one here. So I might say, tell me the quantum numbers for the electron I just circled. So first of all, I want the principal quantum number. N is equal to, we're in energy level 2 here, right? We know that from the 2p. So energy level 2. That's N is equal to 2. Now, what is the L value going to be for that specific electron? So remember we learned that L values can really go from 0 all the way up to n minus 1. But for this specific electron, we know what the L value is specifically. It could be 0 or 1, but I circled an electron. It's in P. Therefore, the L value is 1. The L value is 1, okay? Because I circled that electron, it's in P. 1 indicates that it's in sublevel P. Okay, so I'm just going to erase that and just write L is equal to 1. And now that we know it's L is equal to 1, we know the ML value can be, the range is -1, 0, +1. And so if you remember, this box is -1, this box is 0, this box is +1 by convention. So the best answer to choose for this would be +1. People sometimes write it in different orders because, like I said, they're degenerate. So theoretically, it could be -1, it could be 0 because they could go in different orders. But based on the convention that we're doing, we'll just go with the better answer is +1. That's what we'll go with. But we're not quite done. We also have to indicate its spin because don't forget the other electron in there, the other one next to it, has the same set of quantum numbers, right? So we need to indicate its spin to distinguish it from the other one. And so it's the one spinning down, so we'll have -1/2. Let's do another example here. Let's do the one right next to it, right here. That one. This one's nice and easy because it's in the same box. So we know that if it's in the same box, it has to be N is equal to 2 as well. It's also L is equal to 1 because it's in the P subshell. And then it's in the same box, so ML is +1. The only difference is its spin is opposite. Its spin is up, so +1/2. We'll try one more example. Let's do this one over here, the one I just circled there in orange. So now we're in the 1s. So energy level 1. When you're in energy level 1, you only have S. So L is 0. And that makes it easy. ML will be 0. And because you only have one box there, right? 0. And this is pointing up, so our MS has to be +1/2. So we just gave the set of quantum numbers for specific electrons that I circled within an atom. Remember that these quantum numbers do not tell you the exact location of the electron. You can't know that. It just tells you what orbital region of space it'll likely be in 90% of the time. That's the idea there. So to summarize, let's go to our summary table and complete it. And then afterwards, I'll make a separate video where we'll do a few examples together to learn how to use these quantum numbers. So first of all, in this table, there shouldn't be n is equal to 0. That doesn't exist. You need to have n is equal to 1 at the very least. So when you have n is equal to 1, your only possible L value, because L value goes from 0 all the way up to n minus 1, is 0. When you have n is equal to 2, your possible n values are 0 and 1. And when you have n is equal to 3, your possible n values are 0, 1, and 2. We may as well add n is equal to 4 here. It's going to be a bit messy, but let's do it. We have 0, 1, 2, and 3. Now, our ml values, remember, they go from negative L all the way to positive L. So here, there's no negative or positive 0, just 0. In n is equal to 2, well, L is 0. But if you're at 1, you can have negative 1, 0, positive 1. For 3, well, 0 is just 0. For 1, it's the same thing as in the second shell. For 2, we can have negative 2, negative 1, 0, positive 1, positive 2. And then if you're in the fourth shell, well, same idea. ML is 0 here. Over here, it's going to be negative 1, 0, positive 1. If your L is equal to 2, you're at negative 2, negative 1, 0, positive 1, positive 2. And if you're at L is equal to 3, your ML will be negative 3, negative 2, negative 1, 0, positive 1, positive 2, and lastly, positive 3. I'd like to save the easiest for last here because we're out of energy almost. We have, for MS, doesn't really matter where you are. The only MS values you can have are half, plus or minus half in all situations. So to finish off, this is just a little reminder about the maximum number of electrons in a shell. Remember that the maximum number of electrons in an energy level or shell is going to be 2n squared. And now we know that this n over here really represents the principal quantum number for the shell number that you're in. So you can apply this to this formula to questions like the one over here. What is the maximum number of electrons in the second energy level? So remember, second energy level can really only have an S and P sublevels. And if you recall, S can hold 2 electrons max. I'm not going to draw them in there, but I'm just going to write that down 2. P can hold 2 electrons in each box. So that's 2 plus 2 plus 2 plus 2. That's 8 max. We can figure this out using our formula. So we can say we are in the second energy level, so n is equal to 2. And we can say that the maximum number of electrons is 2 times, replace the n by 2 squared. So that's going to be 2 times 4, which is 8 electrons max in the second shell. So in this video, we learned about the quantum numbers and how they're used to give us a general region or description of the regions of where electrons can be found as a probability. We learned how to write the quantum numbers for specific electrons and how to derive quantum numbers from the principal energy level quantum number, the principal quantum number. So in the next video, we're going to take a look at some examples on how to interpret problems that are related to quantum numbers. And once you understand quantum numbers very well, you'll be able to represent electrons using energy level diagrams, which we've actually been kind of doing sort of when we draw these boxes out. So luckily, it won't be drastically new for you. If you understand quantum numbers today, you'll be on the right path to understanding the energy level diagrams and configurations later on. For practice, you can do the homework found in the learning goals, but you can also go to the visuals found in the learning goals as well. And the visuals have some great pictures that go over the concepts that we just saw here. And there's a link next to this visual that has the answers as well. So try these practice problems out over here. The answers are included in a separate PowerPoint next to the visual. And then you can also try out the the practice Brightspace quiz that's included for you, which you have unlimited attempts for. And just to show you the answer key, so the visual is found right over here, visual and practice quantum numbers, and then the answers is right next to it, or right next to it over here in a PDF that you can open up, and you can go through the answers to make sure you're on the right track. And of course, the homework is listed over here. There's a main worksheet, and there's additional worksheets over here that you can try out if you feel like you need additional practice to understand the concepts.